Hey guys, and welcome back. Today we are talking about the electromagnetic spectrum and how to use a Bohr model of hydrogen in order to solve specific problems. Now, I will say you guys are probably familiar with the electromagnetic spectrum from previous science classes, so we're going to go through the first part pretty quickly. However, I need you guys to pay attention to the end because that is where it's going to get a little bit tricky, and we really need to make sure we're reviewing those examples before jumping into our quiz today. So we want to make sure, move that down, we want to make sure that we're just paying attention, especially at the end, okay? So without further ado, let's go ahead and get started. So today we're talking about the electromagnetic spectrum. We've been focused on the structure of the atom. We know that there are protons and neutrons in the middle, and then those electrons are around the outside, in the electron cloud. Now, the second half of this unit is really focused on the electron, and the electrons emit energy in waves, okay? So these waves show us three things. So the wavelength, how long, the frequency, which is how often, and then the energy, which is how much, okay? So higher frequency and shorter wavelengths are going to mean more energy. Longer wavelengths and longer frequency is going to mean lower energy, okay? So we have our wavelength and our basically frequency. Typically, longer wavelength is lower frequency. Shorter wavelengths are higher frequency. So this blue wave would have a higher energy, and then this green wave would have a lower energy. Okay, so, and we can think about back when we talked about nuclear decay, like those gamma particles, they would have shorter wavelengths, higher frequency, they're high energy. When they pass through us, they can damage our DNA. So there are 7 types. I'm going to go through them really quick. The first one is radio waves. These are the longest waves. They're used in TV antenna and cell phones. They are around us all the time. They're passing through us constantly, and we don't notice them because they are low energy. Next up, we have microwaves. These are the second longest waves, and they are used in microwave ovens and cooking. So when you pop your food in the microwave to heat it up, those waves will pass through the molecules, move them around, increase in kinetic energy, and heat up your food. So it's a modern miracle. Next, we have our infrared waves, also known as IR. These are the third longest waves. They're used in electrical heaters, remote controls, and thermal cameras. So we cannot see infrared waves with our eyesight, so just our normal eyesight. But they do make special cameras and goggles that are thermal energy imaging cameras that you can see infrared rays, but those again are special. We cannot see them with the naked eye. Next is the kind of light that we can see with our naked eye, which is visible light. This is the fourth longest waves, and these are the only waves we can see unassisted. So any of the color that you see, what you pick up with your naked eye, that's going to be falling in the visible light spectrum. And then we have our rainbow bright. So these are the basically distribution of the colors. So we have Roy G. Biv, if you guys remember that from elementary school. These are the colors of the spectrum of visible light that we can see. The longest, from longest to shortest, is going to be red, orange, yellow, green, blue, and violet. What this means is that red wavelengths will have the lowest energy, and then violet will have the highest. Right? Because remember, longer wavelengths are lower energy, shorter wavelengths, higher energy. So red waves, red light will have lower energy, and then all the way up to that blue and violet, that's going to have a little bit higher energy. And then UV light is the third shortest wave. It's used in vitamin D production and also sterilization. If you guys have been in a brick and mortar classroom before, science classroom, you might see the UV sanitation boxes for goggles. They use UV light in like waste treatment plants because it's high energy and basically it runs through the bacteria or the viruses, scrambles up their DNA, and it kills them. Okay, so UV light can be used in sanitation. There are X-rays, which are the second shortest waves. These are used in x-rays and radiation therapy. So if you go to the dentist and get your dental x-rays done, or you break a bone, you have to have something x-rayed at the hospital. If you notice, they put like a lead apron on you and they try to protect your places that are not getting the x-rays because they're very high energy and they can be dangerous. Now with x-rays, it's kind of like dosage and exposure. So if you get one x-ray, or like you get your teeth x-rayed once every few years just to keep them updated, that kind of exposure is not going to do you any harm. But if you are being exposed constantly, so like x-ray technicians, if you've ever noticed, if you have an x-ray, they step outside the door, they step outside the room because consistent exposure to those x-rays could give them cancer. And then here is the full spectrum, going from those radio waves that are longer and less energy all the way up to those gamma rays, which are, we know, high energy emissions from that radioactive decay. Okay, so gamma rays are the shortest waves, and they are used in radioactive resources. Remember, we learned about gamma energy and gamma decay when we talked about nuclear chemistry. With gamma radiation, they're very short wavelengths, very high energy. This is the kind that if you're exposed to, especially for a prolonged period, can really cause damage to your organs, cause damage to your cells and your DNA. Okay, so this is the most dangerous type. All right, so how do these emissions occur? So when electrons are in an excited state, they are in a shell above their normal shell. So remember when we talked about Bohr models, and you guys created those Bohr models where you have the first energy level gets 2, and then you start to add those electrons in the second orbital with 8, the third level, 8 again, so on and so forth. So basically, when an electron's in an excited state, it means it's been pushed up into a level that's above its normal level. So the normal level where the electron usually resides. So it can absorb energy. Those electrons get pushed up and they're in an excited state, okay? Now, eventually, they're going to lose that energy and they're going to give it off when they return to their ground state. And their ground state is just like the level or the energy, that shell that they're supposed to be in, right? So they absorb energy, they get excited, they move up the energy shells, and then when they go back to where they're supposed to be, they have to release that energy, so it's given off, okay? Now, when this happens, so when the electrons go from an excited state to a ground state, they give off energy. Sometimes that energy can be in the form of ultraviolet light, sometimes it can be in infrared light, and sometimes it can be in the visible spectrum. So when we're seeing colors, when we're seeing light, like from the aurora borealis that was in your engage portion of your lesson today, what we're seeing is the emission of that spectra, emission of that energy as those electrons are moving back to their ground state. Okay, so we can use the Bohr model of hydrogen to help us determine what kind of light and what kind of energy is going to be emitted. Okay, so this is where we're learning something new today. Okay, for most of us, the spectrum is a little bit of a review, but this is going to be new to us today in chemistry. Okay, this is how we use the Bohr model for emissions. So you guys have this in your reference tables. If you're using your PDF version, I don't know the exact page, but if you're using the slides version of your reference tables, it's going to be slides 6 and 7 that you use. Okay, so this here is a Bohr model of hydrogen. It just helps us to determine what kind of light is being emitted as these electrons are falling from their excited state into their ground state. Okay, and these are the steps. So step 1, we're going to identify which energy level to start. The problems that you're going to see, it'll tell you where to start. And then step 2, you're going to identify which energy level to end with. So if you see the red dots here on the energy levels, right, these energy levels of the Bohr model, these are the electrons, okay? And the movement of the arrow is showing you what level they're falling to. So for example, I'm just going to use this one right here. All right, I'm going to use this example right here. So you put your cursor or your finger, for you guys at home, it'll probably be a cursor because you are virtual students. So you put your cursor on the level and then you figure out which level it is. So for this one, we're starting at 6. So here's 6, and then it moves from 6, 5, 4, 3. So where the arrow is, this is telling you that this electron has moved from energy level 6 down to energy level 3. Okay, so it's going from an excited state in energy ring 6 to a ground state in 3, okay? So then you can follow that and you can see what the energy level and emission associated with that would be. So if we look at this, that means if an electron goes from level to 6 to level 3, it's going to emit light in the, I believe this is the IR. Yep, so this would emit infrared light. And this particular one I have on these slides is a little bit fuzzy. The one that you guys have in your reference tables is a lot better, okay? So you're going to trace that line down to the number, and then if it's in the visible light tab, you have to use the electromagnetic spectrum to determine the light that is given off, okay? So again, you guys have an example of this in your reference tables that we will be using. Okay, so let's do some examples, and then I'll do another example for you guys in your assignment today because I think that a few of these would be helpful. So the first one says an electron falls from energy level 3 to energy level 1. What type of electromagnetic radiation is emitted? Infrared, visible, or ultraviolet? So I'm going to go to my reference tables just because this one's going to be a little bit easier to use. Remember, these are linked in your virtual materials, and I'm going to link it in your lesson today. Okay, so we're going from 3 to 1. So the first thing I want to do is put my cursor on the 3 and find the electron that falls from 3 to 1. All right, sometimes there will be multiple electrons on 3, so you just have to find the right one. This one goes from 3 to 2, so I know that's not the guy I'm looking for. Here is my guy. He goes from 3 to 1. Remember, where the arrow ends is where you're ending up in your ground state. So this is the electron that's going to fall from 3 to 1. So we're going from an excited state in 3 to a ground state in 1. Then we follow this line down, and the emission energy is going to be 103 nanometers, okay? And if we see, that is categorized as UV light. So the answer is going to be ultraviolet light, all right? So the answer for this example is ultraviolet light. I'm not going to type that in. Actually, yes, I am, because you guys are going to have access to this, but hopefully you are watching this video because that will be very helpful. Okay, now here's the one that can get tricky. It says an electron falls from energy level 5 to energy level 2. What color of visible light is emitted? So you're going to have to use slides 6 and 7, and this one is where we can get tripped up a little bit. So I'm going to try to do it quickly because I'm running out of time on my recorder here. But just like before, we are going to find our electron that's in 5, and then let me check again, going from 5 to 2. Okay, so here is energy level 5. Let me find my electron on 5. And then 5, 4, 3, 2. This is my guy. Okay, so he's falling from 5 to 2. So his emission is 434 nanometers, all right? 434 nanometers. We know it's in the visible spectrum. However, this question asks us to find the correct color. So we are going to have to use our electromagnetic spectrum, okay? You're using this portion of the electromagnetic spectrum. On the bottom, we see our measurements. Now the difference in this is that it's measured in meters. The only thing you have to do for a conversion from nanometers to meters is you're just going to put a decimal point between the first two numbers. Okay, so what I mean by that is that we determined that our measurement here was 434, right? So this is 434 nanometers or 4.34 meters. Right? 4.34 times 10 to the negative 7 meters, okay? So when you're looking for the color, you just have to put the decimal point between the first two, okay? So 4.34 times 10 to the negative 7. So when you're using that spectrum, that is what you're going to do. So we have to find where that falls, okay? So it's 4.34, so we're going from 7.0 up to 4.0. Now, we need to pay attention because this is decreasing, right? So it's 4.3, but we are falling here in this visible range, right? Because it's 4.34, and 4.34 would fall between 4.9 and 4.2. right? Because we're decreasing as we go this way. So to go from here over, we would start with like 4.1. So because it's 4.3, we're going to fall in the blue spectrum. And so the answer to this one is going to be blue. Okay. I'll do another example for you in your assignment today, but that is the gist of that.